Hey guys, in this video I will be talking about special power series called Taylor series and Maclaurin series. These series are special in a sense that if you are given a function which you can differentiate infinitely many times, then you will be able to find the power series representation of that given function. So let's get started. Let us recall that a power series centered at A is of the form sum of Cn times x minus a to the power n and running from 0 to plus infinity. In our last lecture, we were able to find the power series representation of the function 1 over 1 minus x, which is equal to the sum of x to the n and equals 0 to plus infinity, provided that the absolute value of x is less than 1. And also, we were able to construct other power series representations of functions from this identity. So the question now is, do other types of functions have power series representations? And if so, how do we find such representations? So, suppose we have a function f of x, which can be represented by a power series given this form, such that the absolute value of x minus a is less than r. Meaning, this f of x is equal to this power series provided that we have this inequality. Now, if we expand our f of x in the form of the power series, then f of x is equal to c0 plus c sub 1 x minus a plus c sub 2 x minus a squared plus so on and so forth for each x such that absolute value of x minus a is less than r. Now, if we let x equals a, then this one, and all of the terms that have x minus a in it will become 0, and therefore we only have f of a equals c sub 0. Now, during our last discussion, um, if we have a function which can be written as a power series inside the interval such that x minus a in absolute value is less than r, we can differentiate our function. So what we're going to do is to get the derivative of this function, hence the derivative of this function. If we do this, then we will have f prime of x equals c1 plus 2c2 x minus a plus 3c3 x minus a squared plus so on and so forth. And then what we're going to do is to evaluate this at x equals a. If we evaluate this at x equals a, these terms here, they will all become 0. And therefore, f prime of a is just equal to c sub 1. Now, we get the derivative again. F double prime of x will be 2c2 plus 2 times 3c3 times x minus a plus 3 times 4c4 x minus a squared plus so on and so forth. And then if we evaluate this at x equals a again, then all of this will disappear because they will become 0. And therefore, f double prime of a is equal to 2c2. We continue the process. We have the third derivative of f. This is equal to 2 times 3c3 plus 2 times 3 times 4c4 x minus a plus 3 times 4 times 5c5 times x minus a squared plus so on and so forth. And we evaluate this at a so that we will obtain f triple prime of a equals 2 times 3 times c3. If we continue the process, we will have the nth derivative of A, the nth derivative of f evaluated at A. This is equal to 2 times 3 times 4 times so on and so forth times n times Cn. And this one here is just equal to this n factorial. Okay? So notice, nth derivative, this is the last factor here, 2 times 3 times 4, and then times until times n. Third derivative here, we just have 2 times 3. Second derivative, we just have 2. Even if you look at the first derivative here, we just have C1 because we have 1 in here. Okay? F of A, that's C0. There's times 1 in there. But that's also the same as 0 factorial times C sub 0. And of course, 1 factorial is equal to 1. So this one is 1 factorial times C sub 1. So if we now go back to this generalization, it seems that we have the equality f, the nth derivative of f evaluated at A equals n factorial Cn for all n, which means if we isolate C sub n, C sub n is equal to the nth derivative of f evaluated at A divided by n factorial. So why is this helpful? If you remember, our f of x, if it has power series representation, then it can be written as summation of Cn times x minus a to the n from 0 to plus infinity. But now our Cn is equal to the nth derivative of f evaluated at A divided by n factorial. Which means if your function f has a power series representation at A, then your f of x can be written in this form, provided you are working on its interval of convergence. So f of x equals the sum of the nth derivative of f evaluated at A divided by n factorial times x minus a to the n, where n runs from 0 to plus infinity, and such that your x minus a in absolute value is less than r. If we expand this, your f of x is equal to f of a plus f prime of a over 1 factorial times x minus a plus f double prime of a over 2 factorial times x minus a squared plus so on and so forth, provided that your x minus a in absolute value is less than r. And this power series representation is called the Taylor series of f centered at A, or the Taylor series expansion of f centered at A. Okay? So, like I said, it's special because, well, you have a nice way on obtaining the power series representation of your given function, provided that you can differentiate the function infinitely many times in the given interval. Now, if we have n equals 0, of course, we have this what we call the zeroth derivative. The zeroth derivative is actually just the function. So here, the zeroth derivative of f evaluated at A, we'll just write it as f of A. Okay? Now, if your A is equal to 0, meaning the center of the power series is at 0, then we will call the series Maclaurin series of f. So again, if you have a Taylor series, you are required to mention the center. However, if you say Maclaurin series, automatically your center will be at 0. Okay? So these are the two special power series. And notice that one of them is actually much special compared to the other one. In a sense that the other one is just a special case of the Taylor series. Maclaurin series is just a special case of the Taylor series. Okay? So, first, find the Maclaurin series for the function e to the x and determine its radius of convergence. We know that e to the x, it is differentiable infinitely many times because, well, if you start with e to the x, the derivative of e to the x is itself. Second derivative of e to the x is again itself, and so on and so forth. The nth derivative of e to the x is again itself. Since we are looking for the Maclaurin series, we evaluate x at 0. At x equals 0, we have the nth derivative of f of x is equal of f of 0. Let me put that as 0 here. This is equal to e to the 0, which is equal to 1. This means that our Cn, this is the nth derivative evaluated at 0, nth derivative of f evaluated at 0 over n factorial, which is equal to 1 over n factorial. Therefore, your e to the x, this is equal to the sum of f of n, nth derivative of f evaluated at 0 over n factorial, x to the n, and from 0 to plus infinity. But this one is equal to this part here is equal to 1 over n factorial. So we have 1 over n factorial there, then multiply to x to the n, and from 0 to plus infinity. Right? Now, the other question is determine its radius of convergence. If we look back at a previous example that we did, we know that this converges everywhere. Okay? So in this lecture, I'll just say that this is the equality is true for all x in the set of real numbers, but as a practice, determine the radius of convergence of this power series. If this equality is true for all x in the set of real numbers, this means that the radius of convergence, this is equal to infinity. Okay? So now, I want you to memorize this power series. This power series is really, really helpful. Okay? So that's the first Maclaurin series for us, or Taylor series for us. Now, find the Maclaurin series for e to the negative 2x and use it to find this actual sum. Well, from the previous example, we have e to the x. This is equal to the sum x to the n over n factorial, and from 0 to plus infinity, which means that if we replace our x here by negative 2x, all we need to do is to replace this x here by negative 2x. So this one here is e to the negative 2x equals the sum negative 2x to the power n over n factorial, n from 0 to plus infinity. And this one, if we just separate the numbers like negative 2 from the variable x, we will have the sum from 0 to plus infinity, negative 1 to the n, 2 to the n, x to the n, divided by n factorial. So this is our e to the negative 2x. For the second part of the problem, we want to find the exact value of this sum. We have n starting from 0 to plus infinity. We have n starting from 0 to plus infinity here. We have negative 1 to the power n. We have negative 1 to the power n. We have 2 to the n. We have 2 to the n here. We have on the denominator n factorial, and we have this n factorial. What was added here is this 3 to the power n on the denominator. But there, we can use this x to the n. If we let x equals 1/3, then e to the negative 2 times 1/3, this is equal to the sum n from 0 to plus infinity of negative 1 to the n, 2 to the n, 1/3 to the n divided by n factorial. And if we rewrite this, this is equal to the sum n from 0 to plus infinity of negative 1 to the n, 2 to the n over 3 to the n, n factorial. But this one on the left-hand side, this is just e to the negative 2 over 3. So this one here, this is equal to e to the negative 2 over 3. So that is the exact value of this power series. So like what I have mentioned before we cannot actually find actual values of the series we were working on. We were only asked whether the series is convergent or divergent. But now we can actually ask for the actual value of the series. Well, provided that we know a power series representation relating to that series. Okay? Now, we have seen that if f has a power series representation, then it is given by its Taylor series expansion. On the other hand, when is it true that your f of x is equal to its Taylor series? When is it true that your f of x is actually equal to its Taylor series? Of course, in the previous example, I just said that your e to the x, this is equal to the sum x to the n over n factorial, n from 0 to plus infinity. And I am sure that this equality holds for all x in the set of real numbers. But how are we certain that the equality actually holds? That is, if we are given a function f and obtain the series using the Taylor series process, when do we have this equality? To do this, Let us consider the partial sum T sub k, I'll write it as T sub k, of the power series such that your T sub k of x, this is equal to this partial sum, and starting from 0 until k only. So here we have f of a plus f prime of a over 1 factorial x minus a plus f double prime of a over 2 factorial x minus a squared plus so on and so forth, plus only until kth derivative of f evaluated at a over k factorial times x minus a to the power k. We call this the kth degree Taylor polynomial of about a of our function f. Again, kth degree Taylor polynomial of the function f about a or centered at a. It is a polynomial because this is a polynomial, this is a polynomial. If you square this, even if you raise it to the power k, it's still a polynomial. And all other things here, these are just actual numbers. So this one is a polynomial. Kth degree because the highest power here is k, but all the rest here, the highest power for each is less than k. So all in all, the highest power is k. Then we say that f is equal to its Taylor series if your f of x equals the limit of t sub k of x as k approaches infinity. Remember, it is very much similar to what we have before. You have a series an and you considered s sub k, and then this one here, s, which is equal to the limit of s sub k, k from k approaching infinity, and if it is s, or it has a limit equal to s, then the sum an, this is equal to s. So it's very much similar to that one here. Okay? Now, from here, let us define r sub n of x, which is equal to f of x minus t sub n of x. Here we are not yet assuming that your f of x equals the Taylor series expansion. Here, we just define this r sub n, which we will call the error term. This should bring back memories when we discuss approximation of Taylor or of series using alternating series, or the other one, the integral test. So it's the same thing. So this one here is the same as the following. The limit of Tn as n approaches infinity, this is equal to the limit of f of x minus r sub n. So you put this one to the other side, then you put this one to this side. What I'm saying is your Tn of x, this is equal to f of x minus r sub n of x. So if we get this, limit of Tn as n approaches infinity, it's equal to limit of f of x minus Rn as n approaches infinity. And this will be equal to f of x. Take note, your n is the one that is approaching infinity. F of x is like quote-unquote a constant relative to n. So it's just f of x. But this one, suppose there is an answer, we can distribute. So we will have minus limit of Rn as n approaches infinity. Therefore, if your f of x is equal to its Taylor series expansion, then the error term must go to zero as n approaches infinity. Okay? Again, if your f of x is equal to its Taylor series expansion, then the error term must go to zero as n approaches infinity. The same as in how we discussed it in the series without the variable x. Okay? Now, use the fourth degree Taylor polynomial for f of x equals e to the x centered at 0 to approximate the value of e. So we have here e to the x equals sum x to the n over n factorial, and from 0 to plus infinity. We want the fourth degree Taylor polynomial, so we need sum x to the n over n factorial, and from 0 to 4. So this one will be what? 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial. So this is the fourth degree Taylor polynomial for e to the x. We want to approximate the value of e, which means we can let x equals 1. So let us label this as t sub 4 of x. So now, e, this is approximately equal to t sub 4 evaluated at 1. But t sub 4 evaluated at 1, this is just 1 plus 1 plus 1 half plus 3 factorial is 6. So 1 over 6 plus 4 factorial is 24. So 1 over 24. So we can add all of this. We will have here over 24. So 1 plus 1, that's 2. So this will be 48. Plus 1 half, 24. So that's 12. Plus 1 over 6. We want 24. So that will be 4. 1 over 24. Well, of course, that's just 1. So we'll have 48 plus 12, 60 plus 4, 64 plus 1, 65. So this is equal to 65 over 24. So the value of E is approximately 65 over 24. So therefore, E is approximately 65 over 24. Okay? Some more examples. Evaluate integral of e to the negative x squared as an infinite series. This integral here, we don't have a way to get to evaluate it, even if we use the techniques that you already know, without resorting to infinite series. So anyway, your e to the, let's say e to the t, this is the sum, t to the n over n factorial, n from 0 to plus infinity. So if we let t equals negative x squared, then e to the negative x squared, this is the sum, and from 0 to plus infinity, negative x squared to the power n over n factorial, this is equal to the sum, and from 0 to plus infinity, negative 1 to the n, x to the 2n, divided by n factorial, which means the integral of e to the minus x squared dx, this is equal to the integral of the sum, and from 0 to plus infinity of negative 1 to the n over n factorial, x to the 2n dx. This is equal to the sum, negative 1 to the n over n factorial, and from 0 to plus infinity of the integral x to the 2n dx, which is now equal to the sum, and from 0 to plus infinity, negative 1 to the n over n factorial, x to the 2n plus 1 divided by 2n plus 1 plus the arbitrary constant c. Okay? Now, since this one, we don't know the actual function representation, here we do not have to find the actual value of c. Unlike in our last discussion, we have an actual function, ln of 1 plus 2x, so on and so forth, or ln of 1 plus x. We have the actual function ln of 1 plus x, which is equal to some power series. That's why we were able to find the value of c. Or we also have the arctan of x equal to some power series, and we were able to find the actual value of c. But in here, this is an integral. We don't know the actual value, we don't know the actual function, which means that we don't have a way to actually find the exact value of c. So this is the final answer. You can also think of this as, since you are doing an indefinite integral, there's always that plus c. Okay? Now this time, we want to find the value of the definite integral from 0 to 1, correct within an error of 0.001. Let us use what we have found so far from here. So, the integral of e to the negative x squared dx from 0 to 1, this is equal to the series, and from 0 to plus infinity of negative 1 to the n x to the 2n plus 1 divided by 2n plus 1. Oops, I forgot something, the n factorial on the denominator. Let me just add that part. N factorial to n plus 1. There's a plus c, but since this is a definite integral, we are evaluating this from 0 to 1. Right? The value is, at 1, we will have the sum from 0 to plus infinity of negative 1 to the n over n factorial times 2n plus 1 minus evaluated at 0. But take note, the lowest power for your x occurs when n equals 0. And that means you have x to the power 1. So this power series has x for each term. There is no constant term, which means evaluated at 0, it's just 0. So now we have this power, this actual value for this definite integral in the form of power series. But we want to find the value that is correct to within an error of 0.001. So how do we do that? To do that, we need to recall the method we learned about the alternating series, estimation using the alternating series. Because this is an alternating series. Okay? So if we want error r sub n within 0.001. But what do we know about this? The error must be less than b sub n plus 1. If we go back to that one, okay? Let me go back to the theorem that I was talking about. This here. We have an alternating series. The error term r sub n in absolute value is less than or equal to bn plus 1. So if we go back to this one, we need our error term r sub n to be less than 0.001. To satisfy this, we need to find the smallest n such that b sub n plus 1 is strictly less than 0.01. If this is true, since your bn plus 1 is greater than or equal to r sub n, then this inequality here will hold. Now, what is bn? This is our bn. This is our bn here. So we need what? Our bn plus 1. This is equal to 1 over n plus 1 factorial times 2 times n plus 1 plus 1. We want this to be less than 0.001, which is 1 over 1,000. Okay? So from here, we cross multiply our 1,000 must be greater than n plus 1 factorial times 2n plus 2 plus 1. So we just distributed 2 times n plus 1. That's 2n plus 2. That's why we have here 2n plus 2. Then there's a plus 1. Or this one is n plus 1 factorial times 2n plus 3. Sorry, the inequality that I have here is wrong. We need the less than. Your 1000 must be less than this one. So again, let me go back. You cross multiply, so this one should be greater because it will go there. This one will be lesser, go there. So this is the inequality. So we can do some estimation. Let's start with n equals 3. With n equals 3, we have 4 factorial times 6 plus 3. This is equal to what? 4 factorial, that's 24. 4 factorial, that's 24, times 9, which is equal to 216. With n equals 4, we have here 4 plus 1, that becomes 5 factorial, times 4 times 2, that's 8 plus 3. Anyway, 8 plus 3. So this is 5 factorial times 11. 5 factorial, that's equal to 120, times 11. This is equal to 1320. And now this is greater than 1000. Therefore, we choose n equals 4. Therefore, this means that the sum, or the integral 0 from 0 to 1 of e to the minus x squared dx, this is approximately, we choose n equals 4 in our summation here. So the sum from n equals 0 up to 4 of negative 1 to the n over n factorial times 2n plus 1. Okay? So if we try to work on this, well, um, you can use a computer algebra system or your calculator. But you will see that this is the minimum value, minimum value for n, for which this one is correct within an error of 0.001. If you only added up to n equals 3, the error will be outside 0.001. If you added up to 4 times, it becomes within. And of course, if you added more, the error will become much, much smaller. But when you added more, then that's more calculation. Right? Now, we want to find Maclaurin series for cosine x. So in here, we have cosine x. This is our f of x. F prime of x. This is negative sine of x, f double prime of x, this is negative cosine of x, f triple prime of x, this is sine of x. Then the fourth derivative, it will go back to cosine x. Okay? Fourth derivative, it will go back to cosine x. And it will now generate this one again, this one again, this one again, then so on and so forth. We want the Maclaurin series, which means that we need to evaluate this at x equals 0. So let us just write it here. At x equals 0, we have f of 0, this is equal to 1. F prime of 0, this is equal to 0. F double prime of 0, this is equal to negative 1. F triple prime of 0, this is again 0. And of course, the fourth derivative of f evaluated at 0, this is equal to 1. And again, it will cycle. Let us just consider these four things here because it will just go on and on in circles. 1, 0, negative 1, 0, then positive 1, 0, then negative 1, 0. Okay? So if we do this, we have your f of x. This is what we have. F of x, this is equal to, well, we start with 1 plus 0 over 1 factorial x minus 1 over 2 factorial. Let me write this instead of minus 1. I will write this as, okay, a little bit later. We will have here x squared plus 0 over 3 factorial x cubed, then plus 1 over 4 factorial x to the 4 plus 2 more terms, 0 over 5 factorial x to the 5 minus 1 over 6 factorial x to the 6 plus so on and so forth. So it seems that if you got odd n, numerator is 0. So we only see even values for the n. Okay? And this alternates. Positive, negative, positive, negative. The next one is positive, then negative, and so on and so forth. So, we use that observation. Your f of x would be equal to the sum. We have your n from 0 to plus infinity. Since it is alternating, we have negative 1. Since the starting is positive, your n equals 0. Negative 1 to the 0 is positive, so we can put this as negative 1 to the power n. Then we have here, this one here is actually over 0 factorial. But we only see even numbers, 0, 2, 4, 6, and so on and so forth. And to generate even numbers, while your n runs from 0, 1, 2, 3, and so on and so forth, what we can do is to multiply by 2. So this is 2n. And we have the factorial, 2 factorial, 4 factorial, 6 factorial. So 2n times 2n factorial. Are we seeing this? When n equals 0, negative 1 to the 0, that's positive 1. 0 times 2, that's 0, 0 factorial. When n equals 1, negative 1 to the n, that's negative 1, that's negative here. 1 times 2, that's 2, 2 factorial. When n equals 2, negative 1 to the power 2, that's positive. 2 times 2, that's 4, 4 factorial. When n equals 3, negative 1 to the power 3, that's negative 1. 3 times 2, that's 6, 6 factorial. And for the power of x, well, you see, 2, 2, 4, 4, 6, 6. So it seems that it's the same as what the denominator is. So this is to the power 2n. So this is the Maclaurin series for cosine of x. And try to check that this is convergent for all x in the set of real numbers. So this is the equality is true for all x in the set of real numbers. So again, something that you need to memorize. That's bad. Right? Next, we want to find the Maclaurin series for sin x. What do we do? Well, we can use this fact here. This is cosine x. Okay, let me emphasize that. Cosine x equals the power series negative 1 to the n x to the 2n divided by 2n factorial and from 0 to plus infinity, where your x is running from, well, where your x is in the set of real numbers. Right? We have this equality. We can use this to find the Maclaurin series for sin x. And to do that, we just need to get the derivative. We know that the derivative of cosine x, is negative sin x. Derivative of cosine x is negative sin x. So sin x, this is equal to the negative derivative of cosine x. So if we do that, we will have negative derivative of the sum and from 0 to plus infinity of negative 1 to the n x to the 2n over 2n factorial. If we get the derivative of this, we have what? Sum from 0 to plus infinity of negative 1 to the n 2n x to the 2n minus 1 over 2n factorial. But 2n factorial, you can write it as 2n factorial. Let me just write it somewhere else. 2n factorial, this is equal to 2n times 2n minus 1 factorial, which means this 2n here from the denominator, it will cancel the 2n here. Take note that I am starting with n equals 0, not with n equals 1. The reason is, if you go back to this one, we have the constant term, and then the next term that appears is power 2. So if we get the derivative, there will be a power 1. And if you look at this, n equals 0, n equals 0. That's my mistake. Okay, I have to, so erase, 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 I have to start with n equals 1. That's, anyway, that's what we have shown in the theorem. So that should make sense. So again, your constant term, then power 2. If we get the derivative, this will disappear and we will have power 1. If we look at this, we start with n equals 1, n times 2, so 1 times 2, that's 2 minus 1, so that becomes 1. That will become power 1. On the other hand, if I have started with n equals 0, which I was supposed to say earlier, that would be a mistake, because when n equals 0, we will have 0 minus 1. That will be a power negative 1, which is not correct anymore. In any case, we will have summation n from 1 to plus infinity. We have a negative here. This is actually negative 1. So we can bring it inside to have negative 1 raised to n plus 1. And then we will have here x to the 2n minus 1 divided by the 2n will cancel. Like I said, this 2n from here will cancel the 2n here. So the denominator is 2n minus 1 factorial. And notice that this power is the same, still the same as this one here. Now, had we started with n equals 0, the power series can be written as follows. N equals 1. When n equals 1, we will have 1 plus 1, which is 2. Negative 1 to the power 2 is positive 1. So in here, the negative 1 can start, when n starts with 0, negative 1 to the 0 is positive 1. So we can just put the exponent here as n. On the other hand, we have 2n minus 1. When n equals 1, that 2n minus 1 will be positive 1. Now we are starting with n equals 0. Instead of writing 2n minus 1, we will write this as 2n plus 1. When n equals 0, this is 1. When n equals 1, this is 3. Here, when n equals 2, this is 3. And of course, the denominator, the power here, is the same as this one, same with this one. 2n plus 1 factorial. Okay? So you may find in different references that your sin x is equal to this one or this one. But take note, the main difference is the starting point. Okay? So again, I'll just put the summary on the next one here. So your sin x, this is equal to sum, and from 1 to plus infinity, negative 1 to the n, well, n plus 1, x to the 2n minus 1 over 2n minus 1 factorial, or sin x equals the sum, n equals 0 to plus infinity, negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1 factorial. Something that you need to memorize. Okay? Here, evaluate the integral from 0 to 1 cosine x squared as an infinite series. Let us recall cosine x. This means that your cosine x squared, this is the sum, negative 1 to the n, x squared raised to 2n over 2n factorial, and from 0 to plus infinity. But this one becomes the sum, and from 0 to plus infinity, negative 1 to the n, x to the 4n over 2n factorial. So if I integrate this from 0 to 1 of cosine x squared dx, this will just be the integral from 0 to 1 of that sum, negative 1 to the n, x to the 4n over 2n factorial, and from 0 to plus infinity dx. Evaluating, still have the sum from 0 to plus infinity, still have this negative 1 to the n over 2n factorial. If we integrate x to the 4n, that becomes x to the 4n plus 1 divided by 4n plus 1. And we evaluate this from 0 to 1. Your n starts from 0. When n equals 0, 4n plus 1 is 1. So there is no constant term. As expected, because you are integrating. The constant term is your plus c, if you had that plus c. So if we evaluate this from 0 to 1, when x equals 0, it all disappears. So we only need to do x equals 1. So this one will be the sum from 0 to plus infinity of negative 1 to the n divided by 2n factorial times 4n plus 1. So this is the final answer. Okay? As an exercise, As an exercise, try to work on this last slide. With that, thank you. This will be the last. So thank you for the for staying. Thank you for the semester. I'll see you soon.